What is up, strivers? It is time for us to learn Scrypto again. We're going to take an hour, and I've got 5 things that I want to learn about. Resource behaviors, proofs, authorization, access rules, and the wallet connector API. No idea what those things are. I was told that I should learn them when I asked in the Discord. So here we are, and here we go. I'm going to take a second to share the link with some people so that they can participate. Yeah, so I don't expect to code during this. I do expect to potentially read some smart contracts, some Scrypto code, so I can try and understand how the things work. But I don't expect to be writing any code. Oh, last time as well, I learned how to update my resim, which resim is, fetch what's resim? Scrypto execution simulator? Radix execution simulator, there we go. So, I'm gonna double check, make sure I've got the notes up. Learning Scrypto. Yep, so I can cargo install path simulator. I like it. Let's run that real quick, see what happens. I got an error. Okay, I don't know where I installed my cargo. Okay, I will figure that out later, or perhaps that's something important. Oh, you know what? If I do source home. Oh, okay. Whatever. Alright. Let us learn about resource behaviors. Step 1. Resource behaviors. Alright, so I got the docs open here, and I feel like I also want to learn about the gateway. This is a Radix gateway. But resource behavior. Alright, resources have configured behavior which is intrinsically understood by the Radix engine and clearly communicated to consumers such as wallets. The developer is able to specify rules around things like who is able to mint more supply, whether it requires special rights to deposit or withdraw it, and so forth. It is also possible to specify which of these rules can be changed after creation and who is able to change those rules. Okay, that makes a lot of sense. And one of the reasons I wanted to take a step back is because last week I was trying to build out or create something that I don't even think is necessary. Well, scratch that. I actually think it's quite valuable to be able to have some kind of, in Rust it's called a trait that would exist on the NFT metadata. So if there's an NFT that implements a specific trait, I can work with that NFT to perform some specific kind of action. And I think that would be incredibly valuable, incredibly powerful, very useful. I just have no idea if that's possible or how I would even do it. I would assume that based on my learning of Rust last week that I have my trait my NFT metadata struct implement a trait. I don't know if implement is the right word here in Rust. And then I could essentially unpack the NFT metadata that I'm using, or that I have access to, using a box. And a box in Rust is a fat pointer, a pointer to an object that you just don't know the size of. So Rust is very memory efficient, and it tries to compact. My understanding of it is that it tries to compact your data quite a bit, and like storage-wise, so it can be very memory efficient. It can know what's in use and what isn't in use, and it can use what's available efficiently. And that makes Rust very powerful and very fast, because it's a nice low-level language, like a very low-level language that doesn't require you to worry about memory management, which is actually really impressive. I will admit, as a software dev, I am impressed. Very impressed. So, yeah, I don't know if that's possible. I think I asked in the Discord, and I don't know if I got an answer. I feel like I might not have had the proper vocabulary to answer my question. So hopefully by the end of this, I can have perhaps better vocab, and I can ask my question intelligently. Okay, but so we have access control resources. We're going to look at that up. And one of the things I wanted to look up was access rules. I'm curious if access control is a similar concept. We'll find out. So in the default case, resource behaves like a pile of rocks. What a great analogy. That is, it is freely transferable from any party to any other party. No more rocks can be created, and none may be destroyed. Let's make some rocks. Rocks. So we created a fungible name, some rocks, initial supply, we have 100 rocks. So we now have a bucket holding 100 rocks. That's interesting. I think a bucket, if I remember right, a bucket is used to store resources or assets that are in transit. Yes. Buckets store resources in transit. So by the end of this transaction, you would need to slap these here, bucket this. You would need to take from this bucket and slap it into a vault for it to not disappear, potentially. I'm not sure what you'd do. Okay. Yep, resources are temporarily stored in a bucket and eventually stored in a vault, or burned by the end of the execution. Each bucket and vault will hold resources of the same type. You can split or combine quantities of resources, respectively, using the take and put methods on the resource container. So bucket and vault you can take and put. You may also query the quantity of resources within the bucket or vault by calling the amount method. It is important to note that buckets do not define a send method. If you want to send a token to a component, the component needs to define a method which accepts a bucket as input and puts it inside one of its vaults. Okay, so resource behavior. I mean, we gotta take a look at resource behavior. Ledger, mint 5, take 5. The bucket takes 5 and then puts 5. There's a bucket reference. So, okay. There are two kinds of state that a component can contain: data and resources. Data is what you are already familiar with in dealing with typical programming concepts like variables and values. Resources are special. They're a crucial part of how Scrypto makes financial applications and transactions safer and more predictable. Unlike data, once resources are created, they can only be moved from owner to owner, never copied or unintentionally destroyed or lost. Resources must always be stored in special containers, either a vault or a bucket. The Radix engine enforces that no resource can ever be lost. So if I create something in a bucket and it's meant to be used in transit and I don't put that bucket in anything, what happens to it? Curious. We have like physical things, which is why they are used on Radix for all types of assets. Okay. Alright, so I think I have a pretty good idea of resources. Yeah, so there's 3 kinds of resources. Or I guess there's just 2 kinds, but you also have a badge. But a usage pattern where resources used to confer special permissions to the bearer. Yeah, so just a specialized version of a, let's say, a non-fungible. Okay. Sorry, my wife is making some lunch for herself. And if that's noisy, I apologize. 1 bedroom apartment. Alright, access control. So resources can have access permissions individually set on various actions, and by setting or adjusting those permissions on a developer can change the behavior. Okay, so we got fixed supply. Freezable is one in which some authority has the ability to change the permissions on withdrawal and deposit. Interesting. Oh, recallable. That's a fun one. Who may remotely seize the resource from any vault. Huh. Updatable non-fungible data. Who may update individual metadata. Okay, so access rules. Who may take the resource from a vault? Who may put the resource in a vault? Each of these actions can have an arbitrary set of access rules defined, and the system exposes those rules in a manner that off-ledger projects such as wallets can understand. Okay. So yeah, this is access rules. So these are access rules, and they determine who can do a thing. And rule is a macro. That's what this nice little exclamation point means. It means that at compile time, it expands or just creates this function for us as necessary. Now, I'm assuming that the value or just like input of this is that this rule, if this rule is true, then you are able to mint. If otherwise, you deny all. So basically, whoever has this badge has the ability to mint and burn things. The first parameter you provide to the access methods is the rule for applying the action, and the second is the rule that is checked for updating the previous rule. What the? That didn't make sense. Is the rule that is checked for updating the previous rule. The rule macro is where we specify the logic which must evaluate to true in order to perform the action. We can arbitrarily combine different conditions like so. Okay. The first parameter you provided the access methods is the rule for applying the action. Okay, I feel like that sentence can be improved. I'm pretty sure what I said was right. If the rule evaluates to true, then you're allowed to perform that action. The second is the rule that is checked for updating the previous rule. That sentence is also a little weird. Updating the previous rule? What does that mean? Does that mean it's like updating what's here? Or does that mean that it's overriding this? Or like that it's the fallback? I'm going to assume it's the fallback. Like if this isn't satisfied, this is used. I think that makes the most sense. So I'm going to stick with that. That's what my gut's telling me. Pretty sure that's right. I'm not sure. Like this is very interesting to me. Very interesting. So like I could flip this, I think, and I could say like anyone, like I could access rule allow all. Anyone could mint. And then you could potentially put like, let's say a rule here that says if you have a specific kind of badge, you can't mint or you can't burn. And so let's say you're playing a game where your goal is to not, like a hot potato game, and you can essentially prevent people from passing the potato by denying them the ability to burn, whereas everyone else can burn. So that would be interesting. It'd be very interesting. How would that work? I mean, would that work? If this is the fallback, I don't think that would work. But you could flip this and say that, yeah, so you have it, the access rule would be allow all, but if they didn't have your badge access, your badge address, it wouldn't work. I need to look more at this require function. I need to, like the data, I'm still confused on the data structures that are available here. So, okay, so I mean, you got your rule, you can do require n or require super admin. Does that make sense? Two of the badges in the specified vec variable. List of admins is a vec variable. Okay. Okay. But any holder can freely burn. Yeah. Okay, so they allow all, but they access rule deny all. Okay, I don't get this second piece. I don't know why it's here. Or say you want to hand out a token that the user can safely tuck away, but not be able to transfer it after they have done so. Restrict withdraw. Rule deny all. Access rule deny all. Okay. Updating the rules after creating resources. Up until now, we have specified all rules with a second parameter of access rule deny all, which is the default state for any unspecified rule. Okay, so now they're going to get into what it means. Oh, that's what they're saying. That's what they're saying. This rule is checked for updating the previous rule. Got it. Got it. Okay, so this is what allows you to update a rule later on. Cool. Okay, understood. That makes a lot more sense. Glad we just kind of kept on going. Dope. Okay, so we got access rules. We are cruising on access rules here. Okay. Yeah. Locking is a one-way process. There's no going back. Okay. Skip some stuff. Which is also the default state for any unspecified rule. Access rule deny all means that it can never be changed ever. Right. That makes sense. Basically, the second thing, yeah, so this second piece is saying who can update this first piece. I like it. Okay. So this gives you governing permissions or governing capacity. So let's say I have an individual, like a company, and they would like to be able to freeze tokens that are being purchased or sold. They can freeze their token. I assume they would give themselves the ability to do that. Let's say you have a DAO, and you would like to have the DAO be able to freeze the token. They can also do that. That's incredibly powerful. Just built into the system. That's super nice. And then they can resume trading. So like if they're going into maintenance mode or something like that, and they would like to freeze everything, pause, like that is like there's always maintenance that has to happen or some update that has to happen. Like let's say as well that there's a bug in one of their contracts and they want to update that contract. I don't know how updating happens on Scrypto or on Babylon, whatever. But let's say you want to freeze a current token set so that people can't buy and sell, and then essentially mint new tokens for everybody based on like taking a snapshot of what they have currently. You could do that. I don't know if you'd ever need to. Again, if you can update a smart contract, I should say update a blueprint. But I would say the implementations of that blueprint, like, oh, what are they called again? I'm wearing Fertin here. Component. What the fetch? So implementations of the blueprint, the components they wouldn't update, would be my guess, is that they would remain as they were even if the blueprint updated. And so perhaps there's a version control system on the blueprints. That would make a lot of sense to me. So you have the ability to specify the version of a blueprint you want to use. And so people can push out new versions of components to patch bugs. And then people can choose to update their components if they wish and desire. And the system can let you know if components that you're currently using are out of date. Like, I could see a lot of value in that. And then basically different versions, like let's say you wouldn't be able to update, for example, from a version 1.1 to a version 2.x, because semantic versioning, it would break things. And so it can't perform an auto upgrade. That's a good question. I need to write down my questions. Questions. So question number 1. Can you update a blueprint? So, what effect does it have on the components? Can components upgrade? can components specify a version of a blueprint they wish to instantiate with? Yeah, sorry, I know it's not up on the screen. Let's see. So that was question number 1. Question number 2, I don't know that question. Maybe it was already answered. We'll keep going. Okay, but let's stop back over resource behaviors. Specify rules around things. So it sounds like resource behaviors and access rules are kind of like meshed together. It's like resource behaviors is like, oh, we can mint, we can burn, we can transfer, all that good stuff. But we cannot do other things. Whoa, rain fart. What's up? Okay, so I think we've tackled resource behaviors, so that makes sense. Like basically, what can a physical object do? And that's what Radix has kind of been focusing on this entire time, is what can a physical object do, and how can I just programmatically, in a decentralized way, represent that. And, you know, I can really appreciate that. I mean, it makes sense. Like, it's easy to think about it. Access rules is basically determining, like, who can actually do the physical things. So if the object is glued to my hand, I can't give it away, for example. And so the transfer, restrict withdraw, it's like you can't transfer it out, for example. So let's see, you got restrict withdraw, restrict deposit. So this is interesting. I mean, who may put the resource in a vault? That is so interesting. Who may take the resource from a vault? So it's like, I may be able to withdraw, but I can't deposit it? What? What does that even look like? What does that even mean? I don't know. What are the implications of that? Like, let's say that I let you withdraw from a vault, but you can't deposit it unless I give you permission. So you have to request permission from my component, which would give you permission based on, let's say, a specific rule set. So that would be very interesting. I just remember my question. It's like, can NFT metadata implement an interface? Or how would I check to see if NFT metadata has specific properties? It's like thinking of resources as like physical objects. It's like I would love to be able to prove or validate the physical attributes of my object. So like they have the analogy of a rock. And I would love to be able to check and see that this NFT is rocky. In order to make decisions and like have specific components work with rocky attributes or rocky NFTs. So that could be interesting. So like just a simple way to make a standard, for example. So like if you have a royalty-based NFT, and you can only buy and sell that NFT if it implements a specific royalty. And so that's where your restrict withdraw and restrict deposit would come into play, actually. Is like it would restrict deposit unless the royalty creator received their fee. So the royalty that component would validate would be the distributor of the badge that allows you to deposit somewhere else, and would only allow you to deposit if you're doing it in a specific way. So like if they receive like their 2.5% fee, for example, that's how you would potentially do that. That's what I'm seeing, at least. I would love I need a soundboard, someone who actually knows more about this than I do. But definitely something worth trying out. Okay. Who may update? Yeah. Okay. All right. Continuing on with our access rules. So I'm going to mark off resource behaviors. I think I have a pretty good comprehension of that. What's going on there? We have access rules. Okay. So this is where we are. Instead of access rule deny all, you can provide a custom rule with the usual rule macro. The authority you provide here has the ability to update the rule in the future. They can change the rule at will, and at any point, they also have the right to change the rule to deny all states, so it may never again be changed. Locking is a one-way process. There's no going back to a mutable rule once it has been locked. Okay, so basically if I change the rule to like the second rule to deny all, I remove my access. I lock myself out. That makes sense. Be very careful with that then. And maybe don't even give yourself the ability to do that at all. Here's an example of playing around with some rules. Around freezing a token. So initial creation, rule admin is some badge or address we've previously defined. Okay. So rule admin vault.authorize. Okay, authorize is something that I wanna get an understanding of. And that's another thing. Authorization. So we're gonna get into that. Heck fetching, yes, let's go. We're learning all the things right here. Okay, so is a vault that contains the badge allowed to make the following changes. Okay, so rule admin vault. Okay. And these two OR statements, what I would normally see as an OR, is actually a lambda function. Pretty sure. A lambda function with no input. No parameters. So you are authorized inside of that block. Now, generally, in order to authorize, you need a couple of things. I need a signature. I'm going to assume that in Radix they call those proofs. A proof. So I need to have some available validation proof signature that I am the one with access to that vault. Because I don't see how you would authorize. The authorization it seems to be acquired by validating the ownership of some resource. And in order to validate the ownership of a resource, I need to validate that I am the owner of that vault. And to validate that I'm the owner of that vault, I need to validate that I am the one with the private keys with access to that vault. So that's kind of where I think personas as well come in hand. It's like personas specify the keys that you'll need, and maybe it's the special accounts. I don't know. But that's we need some proof, right? So I'm going to assume that at this point in the code, if it actually authorizes, it doesn't throw an error, it doesn't kick me out, that there's some proof available to Scrypto that allows it to validate me. Validate that I am the actual owner of that rule admin vault. And then it hops into this line of code. So we freeze the token so no one may withdraw or deposit. So set depositable, set withdrawable. So only person presenting the proper badge can withdraw or deposit. We unfreeze the token. We lock the token in the unfrozen state so it may never be changed. Okay. This method is available on both vaults and buckets and is used to temporarily put a proof of the underlying resources on the auth zone for authorization. Okay. That whole sentence introduced way more ideas than what I was initially intending. The method takes as parameters a closure, a lambda, with no arguments, and runs it after putting the proofs on the auth zone. Okay, so authorize creates proofs. That's an interesting idea. After running the closure, the proofs are removed from the auth zone. Yeah, so I'm only allowed to make changes inside of this block, inside of this closure. That makes complete sense to me. I would love to understand more about, proof and auth zone. So I'm going to add auth zone to my list of things to learn. auth zone. And that's probably part of authorization. Let's do something crazy and make a non-fungible token which can never be deposited. Right, so we call this a transient token. At this point, you may be wondering what possible use such a thing can have. Well, remember that the Radix engine guarantees that a token can never be dangling at the end of a transaction. Yeah, I expected. Any resource floating around outside of a vault at conclusion of operations will cause the transaction to abort. By handing your caller a token which can never be deposited, which you control the burn authority for, you can compel them to eventually call a method which can burn the token, else the transaction will fail. This allows for really cool stuff like programming a flash loan in an asset-oriented way. We have an example of that linked at the bottom of this page. A flash loan is an obvious example of the utility of transient resources. Loan the money, let the caller do whatever they like, but they must pay you back plus a fee before the transaction is done. But this pattern is also useful for operations where you have an ecosystem of components and you wish to incentivize using them together. Yeah, okay, so that's what I was talking about. Like, if we have the ability, like, let's say that I have an NFT and I want to ensure that a royalty occurs, that they pay my royalty by the end of this transaction. Like, if that NFT is transferring hands, like, they need to pay my royalty, you would use these transient tokens. You would give them the token, which allows them to withdraw. They would have to transfer the token, ensure that actual transaction has occurred. So, like, then they would have to call the component and, like, have it burn the token, and that my component would have to ensure that I received my royalty fee, and then it would burn the crap. It would burn my transient token and allow them to complete the transaction because I validated that I got my royalty. So that's that's really cool. Man, I can really appreciate that. Which, I mean, it makes me think about, actually, like, maybe I've been thinking about this the wrong way. I've been thinking about attaching NFT metadata, like giving NFT metadata a shape, like a known shape. And perhaps the way to do that is through components. It's like, I create a component that mints my NFT collection and manages my NFT collection and ensures that I always get paid my royalty. And so whenever you sell, you must use an auction component or this component, whatever other component that will leverage mine, or, like, ensure that I get my fee, right? So that's what they're saying here, is that you can enforce or force people to use your set of components that will effectively ensure that the functionality you desire is what you want. That's such an interesting way to think about it. That's incredible. It's really cool. I love that. I love learning, and honestly, this is something that I can definitely use for, like, anything and everything that I personally want to do. So, okay. For example, you might have an oracle that receives regular off-ledger price feeds and costs money to keep updated, and costs consumers a fee to fetch price information from. You also control some kind of token selling component. You might set up a specialized entry point on your oracle, which will return a price for free, but also give out a transient token. The only way to burn the transient token is to then pass it to your token selling component, which will burn it as long as a purchase of high enough value is performed. In other words, you can make your oracle free to use for people who use that price information to then make a trade on your other component. Yeah. So you can let people leverage your ecosystem and build out your ecosystem of components so that people can just essentially have options available to them. Makes sense. Okay, so that's access rules. And access rules, I think that makes sense. Proofs, authorization, auth zone still don't make a whole lot of sense. We've got around 15 minutes, maybe 20 minutes left. So let us look at that. So what is the auth zone? The authorization zone. Okay, we saw something important. All scripted documentation is moved to the Babylon documentation site. Okay. I will swap. I guess I was looking at old docs. I hope what I was looking at was good, up to date enough. Access control, resources, off zone. There we go. Alright, perfect. They got proofs in here, they got badge in here, they got... Okay, wait, this is just access control. Okay, they've updated things. Okay, so it looks like access control includes authorization, proofs, all that good stuff, which makes sense, right? Like, that does make sense to me. Okay. Who has it? They also define resource behavior, so, okay. Call address, Scrypto authorization is granted in the form of badges. Any actor is allowed to take a privileged action if the proper authority to do so is present. Yes, I would love more information on that. Badge is a way of referring to a resource that is mainly used for authorization. A badge can be either a fungible or non-fungible resource, depending on your use case. So we can just make a badge. Yeah, so they make it fungible, divisibility none, inner supply 1. Badge into multiple parts. Yeah, makes sense. Curious why you wouldn't just make that an NFT, perhaps because they don't want to apply metadata to it. I could see that. To create a new badge type, we use resource builder. Yeah. Okay, one of the important conventions of badge usage is that under normal circuit usage, they are not actually withdrawn from a vault and passed around. Instead, a proof is created and used to prove that an actor has access to that badge. Okay, I'm going to assume that an actor, they use the word actor here to define an entity interacting with the blockchain. You can create a proof for a particular resource from a vault or a bucket, and then do things with that proof without changing ownership of the underlying contents. Okay, yeah. Holds a Flix token signifying that I'm a member of Radflix. I can create a proof of that token and present it to a Radflix component so that it will allow me to access it. I'm not actually transferring it. Even if the Radflix component was buggy or malicious, it would have no ability to take control of the underlying token from which the proof was generated. Think of it like flashing a badge in the real world. Yeah, makes sense. Proof cannot be created with a quantity of 0. That is, if you have a vault which is configured to hold a specified resource, but the vault is entity, you can't create a proof of that resource. That makes sense. Scenarios where you care about the quantity associated with a proof are unusual. Typically, you simply care whether it is present at all. Okay. So that makes sense. Proof, I'm going to write that down. A proof. I do enjoy good vocab. So, proof. Well, that's my questions. It's not right. Proof. A resource that is used called a badge. A resource that is used to validate. It's not a resource. A data structure? A signature? I'll call it a signature that validates existence of a specified resource in a vault or bucket. I should say, that validates both existence and ownership of a specific resource in a vault or a bucket. I think that's as close as I can get to like a succinct definition of a proof. A signature that validates both existence and ownership of a specific resource in a vault or a bucket. Okay. So, right, the authorization zone. The top level of every transaction, accessible by the transaction manifest, contains a worktop where resources are stored and an authorization zone where proofs are stored. When calling any Scrypto method from the manifest, the rules governing access to that method are automatically compared to the contents of the authorization zone. If the rules can be met, access to the method is granted and the call succeeds. If the rules can't be met, then the transaction immediately aborts. There's no need to specify what proofs you think are necessary to meet the rules. The system just figures it out for you. Okay, that's very nice. The same logic applies within a component called directly from the manifest. If it attempts a privileged action on a resource, such as trying to mint additional supply, the rules are checked against the contents of the authorization zone. If the rules can be met, the action succeeds. If they can't, yeah, okay. You don't have to think about access control or the authorization zone. The system just takes care of it. Okay. So basically, it just, when you're trying to call a function, it gets the rule for that function. It ensures that it looks through the proofs that are available to you at the time of that call. So like, let's say I did my Scrypto admin vault.authorize, and it essentially creates a proof for me inside of that closure. So I mean, that makes sense. There are times when you actually need your code to see what proof a caller is using. For example, what if you issue a non-fungible badge to each of your system members, which contains some metadata like a user ID that your code will care about? In these cases, you add a proof parameter to your method, and your caller can make a clone of a proof sitting in the authorization zone, and then pass it to the method just like any other parameter. Passing by intent. Okay. Mutable self ticket. Make sure the provided proof is of the right resource address. So we validate the proof. Ticket.validate proof self ticket address. Okay, so this is our component we're looking at. And we expect it to be of the right address, otherwise we say the wrong badge is provided. Okay. Get the data associated with the past NFT proof. Non-fungible ticket data. Right, so we get their ticket data. Ticket data to XRD amount, okay. If we didn't, people could send us any NFT that has the field XRD amount and trick our components. Whoa, is that true? People could send us any NFT that has the field XRD amount and trick our components. Whoa. Yeah. So I don't even need to like... What the... Oh, what the... this is blowing my brain. So I don't need... Just... Are structs inherently... Do they inherently define an interface? I struggle to see that actually working in some scenarios. Like, assuming Rust packs data pretty compactly, and I have a struct, and I have an NFT metadata for that struct. Like, I wouldn't see it just this statement being true, but I don't know enough about Rust for it to like intelligently say that, okay, I'm gonna copy this statement. I love that statement. All right. That's awesome. Okay. Oh. Do structs naturally define an interface? That's a very interesting idea that I had not thought of. Any proof passed by intent is validated to ensure that it is of a resource address expected by the component. Therefore, data on a proof is not available prior to validation. Oh. Only once a proof has been validated can its contents and data be visible and usable. Proof validation is typically done against resource address. However, a proof can also be validated. To check that it contains the correct resource address, correct amount of a specific resource, or contains a specific non-fungible ID. Once the proof has been converted to a validated proof, can the data on the proof be accessed and made usable? Okay. Validate resource address belongs to, validate contains, non-fungible global ID, non-fungibles. Okay, so I can validate a group of NFTs actually. That's pretty cool. So that's super nice. A specific amount of a specific resource address. So like, I will token gate you hardcore if you don't have 10 of these. You need to have 10. A lot of people do that actually. Against a resource address and an amount to make sure that the caller is presenting the correct amount of their badge. So they're only presenting one? That's interesting. So you're enforcing that they only present one badge. User badge that validate proof validation mode expect them. Okay. All right. Limitations on proof visibility. Yes. Because proofs provide authorization to privileged methods or resource actions, it's important to understand how they are allowed to move, who can see them, and how they are prevented from being abused by malicious or buggy components. Yeah, I can get behind that. It's like if you give someone your proof, you don't want them to be able to do things with it that you don't want them to do. Does it make sense? Up the call stack as many times as you want, but can only move down the stack once. Okay. Calls a method on component alpha, which returns a proof back to the authorization zone. A later call from your manifest to component Bravo will be able to utilize the proof. But if component Bravo compels component Charlie directly, that proof won't be considered when determining if Charlie's method can be called, and won't be considered for any privileged resource actions within Charlie's method. Got it. So it's assuming a stack, like the call stack then is assuming layers of components that are leveraged to make something occur. Okay. Ooh, excuse me. Okay, that, alright. Okay. I think I get it. The same logic applies when you pass a proof by intent directly in the method parameters. The method you called can see and use the proof for resource actions, but it can't pass it on to another component nor use it for accessing a privileged method. Okay. While executing any called component has its own local authorization zone which it can add or remove from. So if Bravo needs to call a method on Charlie and needs a badge to do so, it will have to create a proof of that badge and place it in its local authorization zone. Stuff you call directly can utilize your authorization zone. Either the transaction authorization zone is if calling directly from the manifest, or the local authorization zone of your component if doing a component-to-component call. If the stuff you called wants to call some other component, then they're on their own for authorization. Okay. Yeah, this last statement is probably the most important piece. If you pass a proof of your user ID to badge to some component, you can be confident that it's not going to be able to call something else and masquerade as you. Yes, so that makes sense. That makes a lot of sense. Basically, from your transaction manifest, you are giving permission only to that one component. Like, I'm assuming your transaction manifest calls. No, we're about to look at it, so we're gonna take a look. I'm just gonna project a little bit here, see what make some guesses. So I'm going to assume that the transaction manifest, what it does is it just has, like, from the video that I watched on the Radix, I forgot the name of it, Piers, and I think his name is Matt, did like they presented on Radix and all the different things that you're going to do and the different layers that they're building out, the Radix engine, the user experience, all that good stuff, and they showed the transaction manifest. And my assumption is that each transaction manifest, like that each element in the transaction manifest is basically calling a function on a component. It's specifying a component, specifying the function to call on that component, and then it just executes that function call. And all of the elements in the transaction manifest have to all execute, or it just doesn't execute at all. It's all or nothing, right? And that's the atomic composability feature that Radix talks about a lot. So, when I provide a proof with my transaction manifest, the proof is only effective for that first component. Once it moves off the first component, it fails. It doesn't work. And so if I'm going to call another component from the original component that I called, like moving down that call stack, it won't work. That's what it says by moving down that call stack. So if I had a second component, this component would need to get permission from the first one or get permission from somewhere else to do what it needs to do. Perhaps be a contract controlled account of some kind, meaning contract controlled account meaning a vault that is governed by a smart contract. And that's where that would kind of make sense. So, okay. That is proofs, that is authorization, that is the auth zone. That makes sense. I would love to get a better idea of the data structure of a proof. For example, I guess like the wallet connector API, I guess I would assume that the wallet can make the transactions. Also, I'm going to assume that the transaction manifest is the thing that I send to the wallet through the wallet connector API. We will find out. This down, transaction manifest. That's the next thing to take a look at. I mean, we're basically already there. All right, the transaction model used not to become the model used for transactions on the Radix mainnet until Babylon is released. Okay, a transaction manifest is the Radix way of building transactions. It makes it possible to compose multiple actions to be executed atomically by describing a sequence of component calls and movements of resources between components. Okay. In short, full atomic composability becomes possible directly in transactions. Makes sense. That's one of the reasons I'm here. I worked on Cadena for a while, and composability of a transaction was definitely not something that existed cross-chain. So I would say that Cadena handles composability like on a single chain, like one single transaction. It handles composability really, really well. It does not, however, do it super well in like across shards. So transaction manifest can also describe the use of badges for authorization to components, payment of transaction fees, and checks on resource amounts to provide guaranteed results for the user. Okay. So basically everything we just looked at, the access control and the proofs, guarantee using the proofs guarantees proofs, and then authorizing those proofs or validating the proof is used to ensure that nothing that you don't expect can happen can happen. The last part of the statement was really bad. Basically, it's validating, like, what you see is what you get. There we go. That is my comprehension. What you see with the proof is what you get with the proof. Transaction manifests are human readable, so that developers or client software can understand what they are signing. When it's time to submit, the transaction manifest is translated into a binary representation and cryptographically signed to create a final transaction that may be efficiently sent to the network and processed by the Radix engine. Yeah, makes sense. Worktop. Read that earlier. Good to get a description. Okay, transaction manifests orchestrate the movement of resources between components. This includes accounts, which are also components that only their owner may withdraw from. This is done through a sequence of instructions using a special instruction set created specifically for this purpose. Transaction manifests do not use Scrypto. Okay. Radix engine processes these instructions in order, and if any step fails for some reason, the entire transaction fails, and none of the steps are committed to the ledger on the Radix network. This is what is meant by the transaction being atomic. All or nothing. Atomic. Execution of a given transaction can be thought of as happening at its own layer, above any components that are called during the transaction. This layer has some special features that make transaction manifests quite powerful. Okay. So transaction manifests are used to create or execute in a layer above components. Interesting way to think about it. Okay, so they have the worktop. Yeah, so the most common instruction in transaction manifest is a component call. And that makes sense. Each call to a component can include data and buckets of resources, and each component may then return resources. The transaction layer itself must always include a way of managing resources between component calls. For this, we introduce the worktop. So while your transaction is being executed, it kind of creates its own pseudo component during the time of the transaction that is able to store effectively your buckets that are in transit and move things into buckets, pass them around, take things out of a bucket, put it into a vault for the end of the transaction, otherwise it fails, right? The transaction layer itself must include a way of managing resources between component calls, so, right? Each transaction is a worktop that is a place the resources may be held during the transaction execution. Resources returned from component calls are automatically put onto the worktop. Perfect. That makes a lot of sense, right? It's like creating a little bubble, little space for you to hold your stuff until you're done, your worktop. I love that word. From there, the manifest may specify that resources in the worktop be put into buckets, so that those buckets may be passed as arguments to other component calls. Okay, interesting. I feel like a component would pass things back in a bucket. I don't know when you would get a resource that doesn't exist inside of a bucket. I feel like they always exist in a bucket or a vault. And I don't know when they would ever be not in one of those. Maybe if you take something out, you'd have to put those somewhere, I guess. So, okay. Yeah. The manifest may also use assert commands to check the contents of the worktop, causing the entire transaction to fail if not enough of the checked resources present. This is useful to guarantee results of a transaction, even if you may be unsure of what a component may return. That makes sense. Hot swapping, or transaction swaps. Transaction swaps, what was I saying? A DEX. Ensuring that you receive the proper amount of resources from a DEX. Of course, we know that all resources must be involved by the end of any transaction, so the transaction manifest creator must ensure that no resources are left hanging around the worktop or in buckets by the end of the manifest steps. Okay, yeah, so clearly you can have a resource that isn't in a bucket. The worktop itself can just hold the resource, so don't lose it. Another feature of the transaction layer is the authorization zone. This is somewhat similar to the worktop, but is used specifically for authorization. So auth zone holds proofs. It proves the possession of a given resource or resources, right? That validates both existence and ownership of a specific resource in a vault or bucket. Yeah. We'll include those. When a component is called by a transaction manifest, the proofs of the transaction's auth zone are automatically passed to that component method's auth rules to be checked to determine if that method may be called or not. Right, so down one. These proofs will include those that are automatically added to the auth zone from virtual badges that are produced by signatures to the transaction. It's how you're able to call the withdraw method on your account component. And so a virtual badge. It's interesting. Yeah, do they create like, so it sounds like a proof is weird. Yeah, virtual badge. If I need to sign my transactions, and that's a virtual badge. Alright, so we already looked at access control. I don't care too much about that. Fee payment. To run a transaction on the Radix network, you have to pay a fee, depending on the number of instructions you are calling and the permanent storage used. Yeah. You do this by locking XRD from a vault that will then be used to pay the fee calculated at the end of a transaction. To lock a fee, you must call a method that essentially calls lock fee amount on a vault containing XRD. There is a method that does this on the account component. You can also call the lock fee on the system component. Okay, that's good for testing. So the fee payment comes from the system rather than your account. Alright, so now we know about the transaction manifest, our worktop. Let's create some definitions. List of actions that take place in order in sequential order on Radix. Uses a worktop to pass resources returned from actions and pass them into future actions. Maybe I should define the word action a bit more here, but I think this is okay for now. The temporary storage location for a transaction. For resources during a transaction. Okay, I like that. And it is now 3:15. That was 1 hour of learning Radix and just cruising through these docs. And I think that was really fetching good. Really needed that to get a good idea of how this all kind of fits together. So we didn't look at any code, well, beyond the code that was here, right? I have a lot more that I need to learn in regards to resim, the Wallet Connector API, the Radix Gateway, but I think that was some fetching good progress. Let's go. Interesting. All right. Thanks so much, guys, for joining in. I really appreciate it. I hope that you have learned things like I have learned things. I kind of just do this just because, I mean, it's fun. I do enjoy learning, and I really do want to use Radix in many different projects that I got going on. So, again, thanks for hopping in, and have a fetching awesome Friday. Let's go.